We built a pretty unique robot this year. There's only a handful of auto clipping robots in the world, and we've gotten a lot of questions about it, so we thought we'd show a little bit behind the curtain of the design process and about how our robot works. All right. First off, introductions. I'm Julian. I was the hardware lead this past season. This is my 4th year on the team. We also have Arnav, who is our lead software person here at CRI. This is his 1st year on the team. Jack and Owen, both 3rd years, and they were on hardware, with Owen being team deputy and Jack being our media lead. And then in the back, our tech person, Josie. She recently joined the team, and she's a hardware member. All right, so first off, the auto clipper strategy. We get questions a lot about how did we come up with this idea so early on in the season. And one of our team's main philosophies is how can we automate as much as possible, taking as much out of driver control and putting it in the hands of our robot. With this, one obvious spot we saw is if you, the robot, can just grab the clips and assemble the specimens all ourselves, that will take a lot out of human hands and potential for human error. Some other advantages of the clipbot strategy are it minimizes driving rather than cycling from the sub to the observation zone. You just are directly parking there and can score. It's very versatile. By cutting out the need for the observation zone, it allows you to drive around really quickly, making it really hard to play defense against or to get blocked off from scoring. And third, it allows for parallelized cycles, primarily during auto. So while we're depositing and clipping, we also have our intake out all ready to grab the next one, which allows us to achieve our 2.2-second cycles. There are a few main challenges we encountered when building a clipbot. The first one is you have many mechanisms mechanically integrated with each other. The intake, the depositor, and the clip mechanism all meet in this one really small point in our robot, which is really hard to get all that stuff working. And due to our parametric CAD, as well as modularizing our subsystems, we were able to figure out the geometry while still improving the individual subsystems. It also required very precise vision because during auto, or the main benefit of a clipbot is during autonomous, because you can score so many points with your fast cycles. However, for that you need really accurate and really fast vision. One way we helped to develop this was with an independent vision development kit, robot, which was just an intake with a camera and the linear extensions and so then, hardware, we were working on developing the core of our robot. Software was working on developing our vision algorithms to get those working to the best of their ability. And then also, finally, the software control over multiple subsystems. With all this stuff working together, you have a lot of systems running at once. And we were able to combat this using Concurrency and the Kotlin library, which Arnav will talk about later. And a lot of that was built upon our previous years of experience. And with that, I'll hand it off to Arnav to talk about some software stuff.
Okay. So, I'm Arnav, and today I'll be talking about vision at first. So as you know, one of our primary things that set us apart from other teams was our auto clipper. And here at Software, we thought, how can we take advantage of this auto clipper and make it the lowest possible cycle times with the best and easiest possible robot to operate? So as Julian said in the previous page, we need precise vision for this. But what exactly does precise vision mean? So we use OpenCV to perform 4 primary steps that we use to transform an image of the submersible into usable data. At first, we flatten the submersible into an undistributed plane. So what does this mean? We take 4 coordinates out of the 4 parts of the submersible, and then we make the image linear so that it maps exactly in how the submersible should be from a bird's eye view. Then we use thresholding, which is basically, as you can see in this image, we have all the red, yellow, and blue samples, and then we pick the pixels that we want of this image. Say we wanted red, as you can see. We make them all white, pixels we want, and everything else darker. So in this case, we made all the pixels that are red, white, and everything else grayscale. Then we find contours, which are basically just clumps of color across the thresholded image of these 3 sample colors, or in this case, which is red. Then we use edge detection and template matching, as you can see in this one, which is basically, we just find the exact XY coordinates and the orientation of each sample so that we can send it to our inverse kinematics. And finally, we have our inverse kinematics, which is just a fancy way of saying, how does your intake know where to go to pick up the block? So for our intake, we have 3 primary things, which are the slide, the angle of the turret, and the turret head. So we basically send the data that we get from our edge detection to the inverse kinematics, so it knows where exactly it needs to pick up the block to have a perfect pickup And then, so this gives us an advantage in both Auton and Teleop because it allows us to have completely autonomous cycles so that we don't have to spend time finding a block and it just does it for us. Okay, so secondly, we have concurrency. So our goal, so concurrency is just a fancy way of saying multitasking, and our goal with concurrency is to maximize the task performed in the lowest amount of time. And so to do this, we use concurrency, which decreases the time we need and optimizes our robot significantly. So for an overview of how our autonomous cycles work with concurrency, we have the vision running always in the background, as you know in the previous page, and we also have prep collect, which basically our intake hovers over the next block we want, and this happens while we're depositing our previous specimen. So according, like in our Auton situation, we have a block in our depositor and it's a specimen. So we have once we deliver it, we have prep collect running, and once it's delivered, we're able to touch the next sample. That's when collect runs, so it basically picks up the block. And then after that we have move and transfer that run at the exact same time. So move is the robot moves 1.3 inches to the right because we want to avoid stacking one or more sample on the same portion of the bar. And then transfer is when the sample moves from our intake to our depositor, and this occurs at the same time. So then we're ready for a clip because we have the sample in our depositor. So once we're ready, we clip the sample with our clipper, and then finally we deliver. And while we deliver, we also have vision, prep collect, and move running simultaneously in the background concurrently, which allows us to have super fast cycles. So this might be very complicated and it's hard to understand, quite frankly. But an overview of this is basically we have an intake that's always collects. Then we have a depositor that stores the block while the clipper clips it, and then the depositor delivers it. And that's how we use concurrency to accomplish 2.2 second cycles. I'm going to be handing it off to Jack for auto clipper overview.
So first I'm just going to go over the main idea for the clipper. So basically, as soon as the rule was added that we were allowed to clip with the robot, we came up with that, or we decided that we were going to do a clipper right away. So we made sure that we allotted space for it on the robot, and in fact we actually designed the entire robot around it. As you can see, it takes up a lot of space on the robot. So we designed the entire robot around it because we figured that it would be very beneficial. We didn't actually know what the clipper was going to look like at the beginning of the season, but we did know that we wanted to have one, so we left space for it, and we designed prototypes in the meantime. So as you can see, over here we have an early version of the clipper. This was an early prototype of it that we used to prove the concept, because we didn't even know for sure if it was possible, but after we proved the concept, we then refined the design. So over there is the current version of the clipper, and then we continued to refine this until it was perfect, and then we just added it onto the robot later. So basically the main design of the clipper is based around like a linear system. So the main clipper portion has this triangular gripper here that holds the clips in the triangular section, and it has a piece of foam that acts as a passive gripper. So that way we don't need any extra servos to hold the clips while clipping. It just kind of sticks in there. This whole piece here is the clipper mechanism, and that is all mounted on a linear system that's able to slide across the robot like this. The advantages of the linear system are that we're able to store 9 clips in here and go to any position to pick them up as we use them. And then we're able to go right here where we actually do the clipping process, and then as soon as we're done, we're able to move out of the way, which allows the depositor to easily get out of the way. So yeah, we use a rack and pinion, a servo-driven rack and pinion based around aluminum linear rails. And lastly, the way that we hold the clips is in this gripper here. We're able to hold 9 in there, and we use a cam, which allows this gripper to be closed without stalling the servo. And then the entire gripper is also coated in non-stick Teflon, which allows us to easily slide the clips out as we use them. So that's an overview of our clipper. I'm going to hand it off to Owen now to talk about that.
Alright. So our CAD is super important in our design process. At the beginning of the year, when we are working with software and we don't have a robot built, we start by prototyping in CAD, printing parts, and we're able to give software this sort of test rig, and they're able to work in parallel with us. And we're able to before we even start beginning to fully assemble a robot, we have a complete CAD model of our mechanisms. This really helps with modeling our transfers. So we have the intake, depositor, and clipper that all need to work together at the same time. And finding these geometries that allows the intake to transfer is really important. So using a full CAD, we were able to find that. Most of our CAD is parametric. So this means that if we adjust one of our variables, for example, the length of our base could update, which would also update the length of our extrusions and the length of our clipper. So this is also helpful for when we added our knife clip. And our entire robot is designed around this clipper. And so, especially once again, simulating this transfer was really important. And with our parametric design, we were able to add on our hang at a later point. After our state championships, we realized that we'd like a hang for Worlds, and we were able to go into our CAD and look at our model and be able to design and iterate on our hang. Another really awesome part of our robot is our antenna mechanism. So right here, we have an antenna. And this is really important because we've designed our robot around our clipper. We need to save space for it. And having belts or strings on our horizontal slides it takes up too much space. So our antenna works. I actually have one of them right here. There are these little teeth on the inside of it, and we have a gear that engages with them, and it's able to push the antenna and extend it out like so, and that is able to extend our horizontal slides. We had issues with engaging, and our coiling, it coils back up into this little tube up here. And this is really helpful for us because of it doesn't have any strings, and it's super and it's fast enough to meet our set. I'll hand it off to Julie.
All right, now just a couple more other things about our robot. Okay, so I'll take a minute to talk about the optical odometry, the SparkFun OTIF sensor, which we're using on our robot this year. There are no dead wheels on our robot. So this works basically like a computer mouse. You got this sensor right here and this really small board. That's like 1.5 inches squared, I think. So it's really small. It was accurate enough for all of our uses this year, which, to be fair, our autonomous was not super complicated. We needed 1 inch or 2 of accuracy, or we had 1 inch or 2 of error that we could allow for, and we have not yet tested it for super precise auto routes. However, it was accurate enough for us. It's also really compact form factor, and you have no mechanical failure points. You don't have axles, encoders, any of that come with the dead wheel odometry pods. Some of the main discoveries we made is having your sensor precisely mounted height-wise to the ground is important. 8 to 10 millimeters is roughly the lenience you have. Outside of that, you get a really drastic fall off with precision, but within that, you're pretty good. It doesn't need to be exactly precise. With 8 to 10 millimeters is important. And it's also important to consider tile sag. So when you set a heavy robot on the foam tiles, it's going to sink a little bit. So in measuring it on a hard table, we found about 11 millimeters is a good spot to aim for to compensate for sag. However, that may vary based on the weight of your robot. You also need to make sure it's rigidly mounted, and we found cleaning it is best with an air puffer like this. Just spray it between matches, and it cleans it really well and keeps it running reliably. A couple other things. Our robot is covered in plastic and polycarb. This is due to Colorado has very low humidity, so we see a lot of ESD events. And by completely isolating our robot, we hope to mitigate a lot of those ESD events from happening. Also, in order to add robot intelligence about whether we picked up a sample or not, we designed and installed a salt stall sensor for our servos. It measures the voltage that's running into the servo, and then through that we can get the current. And using a comparator and a potentiometer, we can set a threshold of current, and once we get that, and then we have a digital output for whether the servo has reached a certain current or not, and then we know it stalls. And that was something different. That was a small little add-on that we've used to help drastically increase the reliability and performance of our automation.